in 6.3, we're talking about how does heat transfer based on all the different ways that it could. So to understand this, we need to first review kinetic molecular theory, which helps explain the behavior of individual gas particles, and the particles could be atoms or molecules, and how they move for reactions to take place. So the first postulate is that particles are so small compared with the distances between them that the volume of individual particles can be assumed to be negligible or zero. That's why we say that the particles, or the volume of gases, is the size of its container. The second postulate is that particles are in constant motion, whether they are vibrating in place or if they are shooting around inside of a container. The particles will collide with the walls of their container, and this is what causes pressure exerted by gas. Number 3, the particles are assumed to exert no force on each other. They are assumed neither to attract nor repel each other. They just bounce off. And then the last one, the average kinetic energy of a collection of gas particles is assumed to be directly proportional to the Kelvin temperature of gas. So a lot of times when we think kinetic molecular theory, it's great to think about it as in gas form because we can see that movement better. But there is still a movement in a solid. It's just vibrations in place. So the particles in a warmer body have a greater average kinetic energy than those in a cooler body, and we see that comparing ice cubes versus boiling water. Boiling water has a lot more motion involved, and so then that makes sense that it has higher kinetic energy if that's the energy of motion than the particles in frozen water. There is still movement that we can't see with our own eyes. They are vibrating. It's thought that absolute zero Kelvin is when there's no movement, but that hasn't been reached yet. So when the particles in thermal contact collide, a transfer of energy can result. And so some terms that you might see for this would be heat transfer, heat exchange, or the transfers of energy as heat in a word problem. And then I have this picture here just to show you that there are different ways that you can actually transfer heat, transfer energy. And so we have some words for this. We have radiation, where the heat would go out through air, like the radiation from the sun would be radiation energy. Conduction is when you're actually touching it, and then convection is when you have this movement of particles. And so what ends up happening when you boil water is it gets hotter on the bottom first, because that's what's usually in contact with your heat source. And so the warmer molecules have more energy, and so they float to the top while the cooler molecules go down to the bottom. And then once they get warm, they push, and it cycles for convection. So if you ever heard of a convection oven, it's the air inside the oven circulates to better move the particles around. But convection would be touching it in contact with touching. So as particles will collide, if they start out at not the same temperature, so over here in my picture, A and B are not the same temperature. Block A has higher temperature, that's why it's red, than block B. Then as they touch, or as they collide, as the particles collide, eventually we have what's called thermal equilibrium reach, which means that the average kinetic energy of both bodies is the same. So then their temperature values will equal out eventually. So an easy way to think about this is putting ice cubes in your water. Eventually, if you have a warm glass of water and you put ice cubes in there, eventually the water cools down, right? Or the temperature evens out. So by having the collision, or having the collide, having them touch, then eventually this thermal equilibrium, or the temperatures are equal to each other, are the same at that time. And so equilibrium, we've discussed it briefly throughout this entire year so far. Equilibrium means that there's no longer a change to our own eyes, but there is still movement happening there. So this leads us into 6.4 with our mathematical calculations with calorimetry, and how if they have reached thermal equilibrium, then the temperatures would be the same at the end.